Good morning, students. Today we are going to learn about some general characteristics of D block elements. These are some of the important characteristics of D block elements. About these characteristics, we are going to learn in detail. In the examination point, they may ask what are transition elements? Write to characteristics of transition elements. Now let's see why transition elements exhibit these properties. We know transition elements involves filling up of d orbitals. And if you take the d orbital, it is of diffused shape compared to Sn p orbital, and it will be projected to the periphery of an atom more than the other orbitals, and hence the d orbitals will be more influenced by the surroundings, as well as it will be affecting the atoms or molecules surrounding them. Hence, the transition elements which are having incomplete d orbitals will be exhibiting these properties. Now let's learn about the physical properties of transition elements. Transition elements are metals. So they will be having high tensile strength. They are malleable, ductile, luxurious, have high thermal and electrical conductivity. They are very hard, low volatile, and they have high melting and boiling point. Let's now discuss about lattice structures of transition metals. Most of the transition elements are hexagonal close packed, cubic close packed, or body centered cubic close packed, which are the characteristics of true metals. Except zinc, cadmium, mercury, and manganese, they have one or more typical metallic structures at room temperature. This is because they have full-filled and half-filled configuration. If you take zinc, cadmium, and mercury, they have full-filled configuration, whereas manganese has half-filled configuration. So their chemistry will revolve more around the s electrons. Therefore, they show more typical metallic structures like s block elements. The next important point is transition metals have very high boiling point and melting point. This is because in transition elements we have more number of unpaired electrons. Both n-1 d electrons and ns electrons are contributed to form strong interatomic metallic bond. So, as the number of unpaired electron increases, the strength of metallic bond also increases. Now let's see in detail about the trends in boiling point and melting point in a series. Look at the graph of 3D series. Melting point initially increases. If you take from titanium to chromium, melting point increases. Then it decreases for manganese. Then you can see a slight increase. Then it falls regularly. Now let's find the reason for it. When you move from titanium to chromium, number of unpaired d electrons available for metallic bonding increases. So the melting point also increases. Then it steeps down to manganese. You may question why manganese has lower melting point though it has many unpaired electrons. If you take manganese, it has half-filled electronic configuration. And we know half-filled electronic configuration is more stable. As a result, 3d electrons of manganese are held tightly by its nucleus. Hence, it will not be available for forming strong metallic bond. Hence, manganese has low melting point than expected. Then when you go to iron, d electrons will start pair up. Hence, number of unpaired electrons available to form interatomic metallic bond decreases. Hence, the melting point also falls regularly. Now let's learn about enthalpy of atomization. It is defined as enthalpy change for the total separation of all the atoms present in an element or compounds. If you take transition elements, they have very high enthalpy of atomization. This is because transition elements have high effective nuclear charge and large number of unpaired electrons. So they form strong interatomic metallic bonds. Hence, large amount of energy is required to separate the atoms. So they have high enthalpy of atomization. Now try to answer why iron has higher enthalpy of atomization than that of copper. Based on its electronic configuration, you will get a clue. If you consider the electronic configuration of iron, it is argon 3d6 4s2. So it will be having 4 unpaired electrons. And if you consider the electronic configuration of copper, it is argon 3d10 4s1. So it has 1 unpaired electrons. If copper is having less number of unpaired electrons, then the number of electrons contributed for interatomic metallic bond will be lesser. Hence it forms weaker interatomic metallic bond and has lesser enthalpy of atomization than iron. Now let's see what happens to the enthalpy of atomization as we move down the series. From the graph you can see 3D series are having lower enthalpy of atomization than the 4D series and 5D series. This is because in 4D series and 5D series, you have the frequent metal-metal bonding formed. This is due to their greater spatial extension of 4D and 5D orbitals as compared to 3D orbitals. Now let's learn about variation in atomic and ionic sizes of transition metals. In a 3D series, ions of same charge show progressive decrease in radii with increasing atomic number. The same trend is observed in the atomic radii of a given series. This is because each time a electron enters a d orbital, the nuclear charge increases by unity. And we know d orbitals have poor shielding effect. Hence, net electrostatic attraction between the nuclear charge and the outermost electron increases. Hence, the atomic radii or ionic radii decreases across the period. If you look at the graph, you can see atomic radii of 3D series decreases from scandium to vanadium as expected. And after that, till copper, atomic radius remains almost the same. Now we will try to understand why atomic radius from vanadium till copper remains almost the same. When you move from vanadium till copper, there are two forces which are acting in opposite direction. One force is a known force to us. It is the effective nuclear charge which pulls the valence electrons towards the nucleus. As a result, the size of the atom will decrease. The second force is the inter-electron repulsion. That is the repulsion between the 3D electrons and 4s electrons. This inter-electron repulsion will try to expand the size of an atom. As a result, atomic radius increases. Since these two forces are acting in opposite direction, they will try to balance each other. Hence, size of an atom will remain almost the same from vanadium till copper. Now look at the atomic radius of zinc. It is larger than expected. If you consider the electronic configuration of zinc, it is argon 3d10 4s2. So in zinc, the 3d orbital is fulfilled as well as 4s orbital is fulfilled. So there exists more inter-electron repulsion. As a result, the orbitals are slightly expanded and its atomic radius is slightly more than expected. Now let's discuss about atomic and ionic radii down the transition series. As expected, when we move down the transition series, atomic and ionic size increases. But there is an unexpected observation, that is, atomic radii of 4D and 5D series remains similar. This is due to lanthanoid contraction, which we will learn in the later part of this chapter. One of the often asked questions in the examination is why atomic radii of third transition series are similar to that of second transition series. Or they may ask why zirconium and osmium have almost similar atomic radii. The answer is due to lanthanoid contraction. It can be explained on the basis of shielding effect. The electrons present in inner shells shields the outer electrons from nuclear charge, making them experience a low effective nuclear charge. The shielding effect exerted by the electrons decreases in the order S has got good shielding effect than P, D and F orbitals. The 4f subshell poorly shields the outer electrons from nuclear attraction, which results in more attractive pull of nucleus on outer electron. In the case of post-lanthanoid elements like 5D series or osmium, the 4f subshell is filled and it is not very effective at shielding the outer shell electrons. Hence, the 4D transition series or zirconium and 5D transition series or osmium have almost similar atomic radii. Now let us learn about ionization enthalpies of transition elements. Ionization enthalpy is the energy required to remove an loosely bound electron from an isolated gaseous atom or ion. As expected, ionization enthalpy increases across the series due to the increase in nuclear charge. Therefore, third ionization enthalpy will have higher value than second ionization enthalpy than first ionization enthalpy. If you take the first transition series, there is irregular trend in their ionization enthalpy. This is because of exchange energy. It is the reorganization of electrons and transfer of s electrons into d orbital. Next, we will see to form metal 2 plus ions from the gaseous atom, which are the enthalpies that are considered. The first enthalpy that we will consider is enthalpy of atomization. Then after forming the gaseous atom, we will try to remove the most loosely bound electron, and that energy required is first ionization enthalpy. Then after forming a monoatomic cation, we will try to remove the next loosely bound electron from it, and that is the second ionization enthalpy. Now let's see why chromium has lower first ionization enthalpy. If you consider the electronic configuration of chromium, it is argon 3d5 4s1. And when chromium loses an electron to form chromium plus ion, it is getting the half-filled stable electronic configuration, that is argon 3d5. So chromium will have the tendency to lose an electron to achieve half-filled stable configuration. Hence, it will be having lower first ionization enthalpy. Similarly, zinc has higher first ionization enthalpy. This can also be explained on the basis of its electronic configuration. If you consider the electronic configuration of zinc, it is argon 3d10 4s2. When it forms zinc plus ion, it is losing its fulfilled stable electronic configuration and it becomes argon 3d10 4s1. So zinc will not have tendency to lose its stable configuration by losing an electron. So, energy required to remove an electron from zinc will be higher. Hence, it has higher first ionization enthalpy. In the same way, you can also understand why manganese has very high third ionization enthalpy. Students, try to answer these questions. Now let us discuss about oxidation states of transition elements. Scandium is the only element in the first transition series to exhibit only one oxidation state, that is +3. All the other elements exhibit variable oxidation states. One of the often asked questions in the board is, why do transition elements show variable oxidation state? If you consider the transition elements, they have their valence electrons in n-1 d and ns orbitals. There is very little energy difference between these orbitals. Hence, electrons from both the energy levels can be used for bond formation. As a result, transition elements exhibit variable oxidation state. At the beginning of the series, +3 oxidation state is stable. If you take scandium, its most stable oxidation state is +3. This is because on losing its 3 electrons, it gets the fulfilled orbitals. But as we move across the series, +2 oxidation state becomes stable. For example, if you take copper, it exists in +2 oxidation state. And the number of oxidation state also increases with the number of unpaired electrons available, and it decreases as the number of paired electrons increases. Hence, the first and last elements show less number of oxidation states, and the middle elements, which are having more number of unpaired electrons, will have more number of oxidation states. For example, if you consider the elements of group 6, chromium, molybdenum and tungsten, the molybdenum and tungsten, which are placed down the series, will have the higher oxidation state, that is +6. That they form molybdenum trioxide and tungsten trioxide as stable compounds. Whereas if you take chromium, in its +6 oxidation state, it is not stable. For example, if you take potassium dichromate, in potassium dichromate, chromium is in +6 oxidation state. And we all know potassium dichromate is a strong oxidizing agent. And this potassium dichromate will be converted to chromic oxide, that is Cr2O3. There, the oxidation state of chromium is converted to +3. One of the difference between transition elements and non-transition elements is their difference in their oxidation states. If you consider the transition elements, they differ in their oxidation state by unity. For example, vanadium has +2, +3, +4 and +5 oxidation state. Whereas non-transition elements differ in their oxidation state by a unit of 2. For example, phosphorus, which has +3 and +5 oxidation state. Another difference between p block elements and d block elements is that in p block elements, lower oxidation states are favored by the elements which are placed at the bottom of the group. Whereas in d block elements, lower oxidation states are favored by the elements which are placed at the top of the series. Students, try to answer these questions.